In previous videos, we had seen that if an object is going around a curve at a constant speed, that its acceleration is perpendicular to its velocity and points in towards the center of curvature. What we haven't done yet is to figure out exactly what the value of the acceleration is. So we've already worked out that the direction is inward, but now we're going to go and work at getting the value. So here I'm going to imagine some object that is moving around uniformly around a circle, like so. And I'm drawing 3 points here. And we can go ahead and put our coordinate system in the middle. That's probably the most that's probably the most straightforward for us. So there's my origin. So since it's in the center, this will be my position. And I'm just going to number these 1, 2, and 3. Just to change things up, I'm going to have my object move around clockwise instead of counterclockwise, but it doesn't matter. This will be R2, and that will be R3. And I've picked these at equal time intervals apart. And since it's, R3. And since it's going at a constant speed, we've worked out if it's going at constant speed and the radius isn't changing, these angles have to be the same. Okay. And we can also similarly work out that our displacement, so I'll call this displacement here, oops, that's not well drawn. Let's try that again. There, something like that. So this displacement here, we'll call delta R1. That displacement there, whoops. That displacement there, we'll call delta R2. And where I'm going with this is I want to find my velocity V1 and V2 immediately before and after this point in the middle here, which that point in the middle is getting a little hard to see, sorry. So I can figure out the magnitude and the direction of the acceleration. Now we've already worked out from before that the acceleration at this point is going to point into the center. We'll go ahead and confirm that. And like I said, we'll actually also figure out what the value is. So let's go ahead and figure out this delta R1. And it'll be the same deal for delta R2. But let's go ahead and imagine taking the vector difference of the two. So to find my delta R1, that would be R2 here minus R1 here. So I'll go and draw my R2. That's straight up and vertical, like that. And then to subtract R1, I'm going to add negative, there we go, R1 like so. So that's R2, that's negative R1. This angle is also that angle there. And actually, let me put that in green just so we can continue to tell them apart. And so this is my delta R1. And I could do the same thing finding delta R2, but I'm not really too stressed out about that. You'll get this result here. And the length will be the same because the angle here is the same. These two lengths are the same. So this triangle here and the corresponding triangle we would have to find delta R2 are similar triangles. And since the lengths of the radii are the same, the delta R's have the same length. So that tells us the speed doesn't change, which we already knew. Okay, but this also means that the velocity over this time interval the average velocity is going to point like so. We'll call that V1. And similarly, V2 would point down and to the right. The same angle that V1 was pointing up and to the right. Like so. And these are technically average velocities, but the game we're going to play is that eventually we're going to say that the time intervals are extraordinarily small. And as we make the time intervals smaller and smaller, this position that we're considering will have to get closer and closer to the point we want to find the acceleration at. And similarly, this one will get closer and closer going the other way as we think about a sequence of shorter and shorter time intervals. But anyway, we can go ahead and figure out the direction of our acceleration. So delta V would be V2 minus V1. So we would go ahead and draw in our V2. And we would add to that negative V1 like so. And that will give us, that's a nice color. That will give us delta V pointing down. And delta V will be pointing in the same direction as our acceleration. So we showed that sure enough, at the top of the circle, the acceleration points straight down. But now we're going to go and start to figure out what the value is. So the first bit here is to realize you can do a little bit of geometry and you can work out that this angle right here is this angle here, is these angles here. So what this means is this triangle here, mostly in purple, and this triangle here, mostly in orange, are similar triangles. So this means that I can write that delta V is to either of these V's. Because remember, since we're going at constant speed, the magnitude of V1 and V2 is just V. That has to equal the ratio of delta R, and it doesn't matter if it's delta R1 or delta R2, so we'll just call it delta R, over R, and it doesn't matter if it's R1, R2, or R3. So that's true by similar triangles. Oops, and I meant to make these purple. There we go. Now, if we go and take a look here at this delta V, we remember that the acceleration is equal to delta V over delta T. So I can rewrite this that delta V is equal to A delta T. And I'm going to go and stick that in right there. So this is going to give me A delta T over V equals delta R over R. And then we're going to have to do a little bit of a cheat, but it becomes legit. So here, this delta R is the displacement between this point and this point. It's always going to be shorter than the arc length traveled. But what I'm hoping you can convince yourself of is as we make the time interval ever smaller, so this angle gets ever smaller, the difference between what's being traveled by the arc length versus the straight line displacement will get ever less. You can kind of see that, say if I have a chunk of arc like this, here, the difference between the arc length and the displacement is quite profound. If I pick just this right here, you can already, oops, if I can draw right, you can already see that it's becoming very hard to tell the straight line from the curve. And as these angles get ever smaller and smaller, that becomes true. In fact, mathematicians have proven that that is the case. So we're going to say that as our time intervals get really short, we can very accurately approximate, and in the limit of the time interval approaching 0, this approximately will become an equal sign again, delta S over R. Okay, so where is that taking us? Where that's taking us is, if we just solve for the acceleration now, let's see, I'm going to have to multiply by V, and I'll keep this over R here, and then I have delta S, and I'll divide by delta T, and I go, oh hey, remember from the tangential speed stuff that that's also the speed. So what we can write is that the magnitude of this acceleration, what we call the centripetal acceleration, not the same thing centrifugal, more on that later, will be equal to V squared over R. And centripetal if you break the Greek roots apart, it literally means center seeking. So it's that component of the acceleration that's pointed straight into the center of curvature. Now, if this is changing speed, we'll have another component. We'll worry about that in a future video. But for now, if you're going around at a constant speed, the acceleration is perpendicular to the motion everywhere and is equal to V squared over R. Now, a useful trick to remember is that we did show that the tangential velocity could also be written as R omega. So if I put that in, so this will become R squared omega squared over R, cancel, cancel. I get that the centripetal acceleration can also be written as R omega squared. Now, I personally find that's about a 50-50 shot which of these is going to be more convenient in a particular situation. So I recommend gaining facility with both. Now, if you check the units over here, you see you have meters per second. You square that, you'll have meters squared over seconds squared, divide by meters per second squared, all good. But if you look over here, you might not be quite so convinced. After all, the units of, so we expect to have meters per second squared because we have an acceleration. Here, okay, the radius, that's meters, that's good. Now this is radians per second, and then we're squaring it, so we have to square both the radian and the second. And that might look problematic, but again, remember, radian is just a placeholder symbol that reminds you that you're dealing with an angle. And even here, though we have two powers of them, the prescription is still the same. When checking units, replace radian with 1. That gives us 1 squared. 1 squared is, well, 1. And so sure enough, I have meters per second squared, and the units do indeed check. So just keep in mind, we only ever just write radian just to remind us that it's an angular quantity. But we are free to drop them when it's no longer an angular quantity. Okay, let's go ahead and do a couple of examples to make this a little more concrete. So the first example I'm imagining is we're going to be looking straight down on top of a countertop or something like that that has a hole drilled in the middle. And through that hole, you tied a string onto a knot. And on the other end of the string, you tied the other end of the string around a washer. Like so. All right. So let's just say that the washer, which will approximate as the washer is going around at, which will approximate as a point mass. Let's say that the mass of the washer is 10 grams, and we'll say it's going around in a 10 centimeter circle. The manufacturer says that for this particular length of string, that if I put more than 50 newtons of force on it, it will break. So what I want to know is, what's the fastest I can spin that washer around before it breaks? Okay, so let's start by drawing a free body diagram for our washer. Okay, we got the tension. There is a normal force and a force of gravity, but the normal force is coming out of the screen, gravity is coming into the screen, and they cancel out anyway. So for the bit of it, for in the plane of motion, all we care about is the tension. So Newton's second law is going to be pretty straightforward. The net force is the tension. That has to equal ma. But we just worked out, if we're going around in a circle at a constant speed, let's say it was counterclockwise here, that acceleration will always be equal to v squared over r. That is the acceleration of something going around a circle at speed v at radius r. Or the central part of it anyway. So we can solve for the speed. That's going to involve, so v squared, let's see, times by r divided by m. Then we can take the square root of both sides. V equals square root of t r over m. So we said that the maximum tension we could have was 50 newtons. 10 centimeters, that's 0.1 meters. I said the washer is 10 grams, so that's 0.01 kilograms. And remember, it's important here to convert the centimeters into meters and the grams into kilograms, because a newton, remember, is a kilogram meter per second squared. And so in order to have your units work out, you have to get your mass and radius into units compatible with that. All right, so if we go ahead and crunch that through, we get that our speed is 22.4 meters per second. So it's whipping on pretty hard before it breaks. Okay. The next example is going to be a little more complicated. It's a classic called the Conical Pendulum. The reason why it gets called a pendulum gets a little complicated. But basically what it is, you can make one by, say, taking a string, you tie the string to the ceiling or to a support. Say maybe you use a lab stopper here and just thread the string through the hole in the test tube stopper, something like that. What you do is you set it up so that it's orbiting around in the horizontal plane. So this circle here is in the horizontal plane, which that plane is technically in and out of the screen, but I'm trying to draw in 3D. So maybe I will do something like that just to help guide the eye a bit. So this isn't an actual surface. I'm just trying to show that that's sitting in a horizontal plane. All right. Let's say the radius of our orbit is 1 meter. And let's say that our stopper is moving at 5 meters per second. What I would like to know is what is the angle with respect to the vertical that the string is hanging at. Okay, so once again here we can do a force identification diagram on our stopper. So draw a circle around the stopper. It cuts through the string, so there's a tension. That's it. Long range force, the usual suspect, gravity. And we're neglecting air resistance and all that good stuff. All right, so we can go ahead and draw a free body diagram for our stopper. So we will have the force of gravity straight down. And if we're doing it right at this instant here, the tension is up and to the right like so. This will always be true for the angle, for the plane that includes the string. And you can do a little bit of geometry to show that this angle is that angle theta right there. Okay. So then this is the tension, the force due to tension in the string. All right. So since the height isn't changing, the acceleration in y is 0. So the acceleration is just purely in the horizontal plane directed towards the center of the circle. So making our usual up, down, right, left coordinate system is the way to go. We don't want to do any tilting shenanigans here. So let's start with the, let's do the x. Okay, well, let's just start with Newton's second law. F net equals ma. So we'll do this as a vectors. T plus fg equals ma. And now we will go ahead and take the components of this. So in the land of x, this will be tx plus fgx equals max. All right, well, the tension, so here we're going to need the x component of the tension. So let's start to draw that in. So there's my tx, that's going to be my ty. So this is the opposite to the angle I have. The tension itself is the hypotenuse. So that's going to be a t sine theta. There is no component, x component gravity, because gravity is entirely vertical. All the acceleration is horizontal, but we can take this just one step further. We know that since we're moving at constant speed in a circle, we know that that's equal to v squared over r. So we can do that. This sometimes gets called here. Sometimes authors will call this piece right here the centripetal force in the problem. I tend not to make that big of a deal of that name, but the centripetal force is the force or piece, is basically all the forces or pieces of forces that you have to add up parallel or anti-parallel to the acceleration to figure out to figure out what that acceleration is. So here, this horizontal bit of tension is what's responsible for making the stopper go in a circle. So that gets the name centripetal force. Important thing to remember here, if you've run across that term before, is that centripetal forces are things you identify. They are not in and of themselves some sort of force of nature or anything like that. So there is no force of nature named centripetal. As one of my professors used to say, Mr. and Mrs. Centripetal are dead. In other words, there's no force of nature named centripetal. There's no person named centripetal. Centripetal forces are things you identify. In this case, the horizontal component of tension we would identify as being our centripetal force. Okay. Anyway, this leaves us with t, which we don't know, sine theta, we don't know theta either, equals mv squared over r. All right, well, hopefully the y equation of motion will take us somewhere to get rid of those pesky t's. So here we take our same vector equation of motion, but now we write the y component. So this will be ty plus fgy equals may. Well, the acceleration is directed entirely horizontally in the x, so the y component of acceleration is 0. For ty, you go look at this bit right here. That's the adjacent, and again, the tension itself is the hypotenuse. So we would write that ty is t cosine theta. Plus, and then, or sorry, minus, because gravity is directed straight down, and it's all of it. So we just say minus fg equals 0. Or we could write t cosine theta equals fg, or t cosine theta, putting in our model of gravity, equals mg. Okay, so now we've got two equations that relate our unknown t and our unknown theta. And again, you could certainly go and solve one of them for t and stick it into the other. And you'll get the answer. But again, I'm going to just show an algebra trick that makes this go maybe a little bit faster. And that the trick here is because you got t times some stuff here, t times some stuff here. If you divide the equations by each other, you can make the t go bye-bye. So let's see what that looks like. So we had t sine theta equals mv squared over r. And what we're going to do is we're going to divide the left-hand side by t cosine theta. On the right-hand side, we're going to divide that by what it's equal to, mg. Now, hey, check out what happens. First off, the tensions cancel, which is what we wanted. Secondly, added bonus, since I never told you what the mass was, it's a good thing that it cancels here. All right, then from here, we can do a quick bit of trig to remember that sine over cosine is tangent. And so now here, when you've got a complex fraction like this, remember to bring this g upstairs. You have to multiply top and bottom by 1 over g. Cancel, cancel. And this leaves you with v squared over rg, like that. So to get the angle, we have to take the arctangent of both sides. Remember, the arctangent is just the inverse of the tangent function. Okay, and now we can put in the numbers. So this will be the arctangent of 5 meters per second, which will square, over our 1 meter radius, and 9.8 newtons per kilogram. And right away, we're going to go ahead and note, for purposes of balancing units, that a newton per kilogram is dimensionally a meter per second squared. So here, when I square this, I have meters squared over seconds squared. Here I'll have meters times meters per second squared. So in both the numerator and the denominator, I have meters squared over seconds squared. So it all cancels. I'm just taking the arctangent of a number, which is what I have to have happen because it does not make sense to take the arctangent of a unit. So anyway, when you find this number and you punch it in your calculator, you get that the angle is 68.6 degrees. Okay. Now this may seem a bit of a contrived example, but there are other practical situations which, although they look different, are functionally the same thing. For instance, you might have noticed that at high-speed racetracks, that the track itself gets heavily banked as the car goes around a curve. Maybe not quite that bad, but like 30 degrees banking is not unheard of in some super speedways. So, really steep banking. And what's the point of that? Well, say you've got a race car here. Let's see, a race car needs a wing, I guess. Sure, and a front wing. Okay, I tried. This is a race car, and you know it is because I labeled it. All right, so if we were to go ahead and look at this, we can draw a force identification diagram for this. And what we will have is, let's see, contact forces here will have a normal force, possibly a force of static friction. Remember, when tires are operating normally, it's static friction. And there's a force of drag, but I'm more interested in the wings on the race car. There is a force of lift, and the direction of the lift might be a little surprising. And then, of course, there's the usual suspect, gravity. So the idea is you don't want to beat up your tires. So part of the reason why they bank the racetrack is to help minimize beating up your tires. The goal is to try to make the force of friction approximately 0. So what's getting us around the racetrack then? Well, if you don't have wings on the car at all, it's just going to look like this. Hey, that's exactly the same free body diagram I drew, except instead of a tension in the string, it's the normal force from the road. So it turns out the horizontal component of the normal force from the road makes it go around. Well, what if you want to go around quicker? Well, what you do is you bolt airplane wings onto the car, basically, but you point them upside down. By pointing them upside down, you'll get a force of lift pushing it into the road, which then forces the normal force to become even bigger, which means you'll have an even bigger horizontal component of force, which means you can go around even faster around the curve. So this is both why racetracks often have banking and also why race cars have wings on them. It's oddly enough to push the car into the road so that the road has to push up even harder to help turn it. No, sorry, I misspoke there. The downforce has entirely to do with the friction, my bad. So if we do need to rely on static friction, we have a bigger normal force, which helps to contribute. Obviously, the horizontal bits of lift and normal force will have to cancel, but it'll give us more friction. So if we are on the edge, we can use static friction to help make the turn as well. Sorry about that there. Another example, maybe even less obvious, is an airplane making a churn. If you ever watch an aircraft make a churn, and if you thought my race car was bad, wait till you see my aircraft. There we go. That's about as good as it's going to get. I guess maybe we could try to give it a propeller. There we go. So again, same deal. The aircraft is trying to make a turn in the horizontal direction. It turns out that the free body diagram here, at least for the churning bit, is gravity down, and then you'll have a force of lift again perpendicular to the wings. We'll get into lift a little bit when we talk about fluids later on. But the point here is that the free body diagram looks the same. So the way an airplane actually churns is by banking, as the pilots call it, the airplane. And that helps to provide the necessary lift to give you a horizontal component of force to make you go around the curve. Now, why is there still a rudder on the vertical stabilizer back here? The rudder is used actually to make sure that the airplane actually points tangent to the curve. So if the rudder weren't there to help twist the airplane around, the airplane wouldn't be pointing in the same direction it was trying to churn. This leads to a condition that pilots call a skid, which is uncoordinated flight. And if that skid gets out of control, things can get really bad. So they apply a little bit of rudder just to keep things pointing the right way. Okay. So I'll finish up here with a bit of a rant about fictitious forces. And I will put those in quotation marks. If I had my druthers, I wish that physics books wouldn't mention them at all at the introductory level. But they do, so we need to talk about it a little bit. So you may have heard of terms like centrifugal force. This is an example of a fictitious force. And by fictitious literally means that, it isn't real. And it definitely isn't real in the sense that it isn't a force of nature. So let's say you're driving around a curve. Let's have the road curve like this. So now when you're going around the curve, as you turn to the left, so the car is doing one of these numbers here as we go to the left. By Newton's first law of motion, so the force of static friction on the tires here is primarily what's going to be making us go around the churn. Probably not much in the way of any banking, just because most roads that we drive down aren't really banked very much, just enough to let water run off them. So anyway, the force of static friction is turning the car around, but let's look at you. What's turning you around? Well, by Newton's first law of motion, you want to move in a straight line. So you're sensing literally the other side of the car moving in toward you. And so you get this sensation that you're being thrown out of the car. Now, what's really going on here? Well, let's go, and my apologies in advance, I cannot draw human forms very well at all. Let's look at your car seat. So the car seat's attached to the car. So the car is going around in a curve. So therefore the car seat's going around in a curve. Now what's making your butt go around the curve? Turns out it's a combination of the seat belt and the bolsters on the side of the car seat. So here you are sitting in the car seat, and I am intentionally tilting you over just for some clarity. So there is a normal force from the car seat pointing to help make your butt go around the curve. That's providing the centripetal force to make that happen. But then you got to ask yourself, what's going to make your neck go around in the curve? And it turns out that your body is actually going to have to be tilted. By Newton's first law of motion, your head is going to want to move forward. And it will for a little bit. And the upshot here is that it actually extends your spine and your neck, especially your neck, just a little bit. So as a result, your head will feel a force of tension from all the ligaments in your spine directed in like that. The horizontal component of the tension here is what is going to make your head go around the curve, because that's what's pointed into the curve. So your body actually has to kind of tilt over a little bit. Wearing shoulder belts will help with that, because then there will be normal and friction forces from the shoulder belt, and so then your body won't have to lean over as much side to side. But even so, if you were to look, say, at professional race car drivers, They were very elaborate seatbelt systems, usually 5-point harness systems, so they're strapped in real tight into the chair, but their neck is still free to move. And it was found that making such high-speed churns, for as many churns as gets made in a racing career, was doing serious damage to necks. Especially if they got into accidents when the neck is already stressed and then something weird happens. So virtually every racing series now mandates something called a HANS device, which stands for Head and Neck System, HANS. And the exact details of how these work depend very much on the style of racing, but they all amount to the same thing. They somehow basically create an extra little bit of artificial spine, if you will. The device itself will clamp the helmet of the driver to their shoulders somewhat. And so this minimizes how much the neck needs to stretch because the straps, or however it works in the particular design, the straps or the carbon fiber or whatever, don't need to stretch anywhere near as much to be able to provide the same tension force, thus reducing the possibility of neck injury. All this to say, though, is that you are feeling your spine lengthen out. And so it certainly feels like you're being thrown to the outside of the curve. And so that is what people will call a centrifugal force. But really, what's at issue here is if you're trying to call that a force, what you're doing is you're trying to pretend that when you're going around the curve that you're an inertial observer, but you're not. Your velocity is changing because even if you're going at a constant speed, remember your direction is changing, so you're an accelerated observer. And in the Newtonian framework, accelerated observers are not allowed to quote-unquote do physics calculations. So from the perspective of an inertial observer, this was how you would explain it. And then they would say that the inertial observer would say that the person in the car, because they're feeling their spine getting lengthened out and the fact that their head was continuing to move forward until their spine lengthened out in order to help turn their head around the curve, that's what's giving them the sensation of feeling like they're being thrown out. Now, sometimes it's useful to pretend that even though you are on an accelerated frame, it's useful to pretend that you're not. For instance, we're all on the surface of the Earth, which is a rotating object. So if you think about it, we're sitting on a rotating object. This means we're all moving around in a circle once every 24 hours. Now, a lot of the time for things that we do, we can go ahead and pretend that we're not accelerated, but the reality is we are. And sometimes things like this matter. And so if you want, for convenience, pretend you're not accelerated, in more advanced treatments, you can show that you need to add up to 4 fictitious forces to allow you to pretend that you're not accelerated, even though you really are. For those keeping score at home, it's the inertial force, the centrifugal force, the Coriolis force, and the transverse force. So I felt the need to talk about this a bit because since books tend to bring it up, I sort of wish they wouldn't bring it up at all and we just talk about purely from an inertial observer framework. But because it does tend to get brought up, I feel that it's actually worth getting into just a little more so that we can then acknowledge that we're never going to worry about it again. So there is no actual physical force of nature named inertial, centrifugal, transverse, or Coriolis. These are mathematical fictions to allow you to pretend that you're not accelerated even though you actually are. And sometimes that makes computations more convenient. But those things are beyond the scope of this treatment. All right, in the next video series, we will take a look at Newton's law of universal gravitation and start to make things orbit. Have a good one.